Okay, welcome back. Sorry to take you through the first section a little bit longer than we had planned. These next series, I think just 4 slides, just to introduce you to the concept of the Immunome Browser, which has been mentioned multiple times, but it's a very powerful and useful tool. We mention it here today because it is the only tool that is integrated into the search interface. So it's accessed at the level of results on the results page. Julia will be going through this in great detail right after this introduction, so I'm just going to give you just an introduction of what it is, what's the Immunome Browser. The immunome is the totality of immune reactivities at the organism level, so the reactivities to the proteome, all right? What is it for? The reason why we developed this tool is because we were very often approached or asked, can you tell me what the immunodominant epitopes are? And that is not a straightforward question to answer, because it depends. It depends on the host, it depends on the scenario. So the one thing that we could use, one bit of data that we could use that is in the database to kind of get at this is that very often the authors will report response frequency. So the number of respondents over the number tested. So then you have a response frequency. And what this data gives you is an indication of the epitope's prominence in that particular host. All right? So how does this work? Well, the Immunome Browser plots the response frequency score, or the RF score, of the epitopes from a particular query. So this is, again, at the level of the results page. So it takes the information, all the epitopes from your query, and plots them along the length of the antigen, all of the antigens in the case if it's the entire reference from a reference proteome. All right? So the reason why we did this, and the reason why it's really nice, is that it's designed to provide you with not just identify epitopes, but also visualize them and an optimized subset of using your specific input criteria. So you can make it very stringent or you can make it very broad. I'm going to show you an example using HCV so you get an idea of this. HCV is a very good example, and I'll explain why. This is the HCV proteome up here. This is what we mean by the proteome, so all the proteins that are expressed from the genome. Hepatitis C virus has a polyprotein that is 3,000 amino acids long. If you do a search on HCV in the database, you get 3,987 epitopes. There can't be more epitopes, logically, right? There cannot be more epitopes than there are amino acids in the genome. Also, you can't possibly assume for any given host that every single one is an epitope, right? What this shows you is that there's an abundance of data. There's an abundance of data that is iterative. So multiple labs, multiple hosts, many different animal models, many different assays. That's why you see so much data. It doesn't mean that every single amino acid in the genome is an epitope for the particular host it's talking about. I'm going to pull this down. So how can you see the trees in the forest? Using your query input. So you can be very selective, you can be very broad, or very stringent. And I'll show you this, a quick example of what this looks like when you plot the HCV data, and then Julia will be going in great detail about how all of it works and all the details of the calculations that are made. So from the home page, if you were to type in HCV, the autocomplete will give you a list of possibilities. You click on one, you hit search. The results page will show you here 3,000, almost 4,000 epitopes. If you click on the antigen page, you'll see genomic polyprotein. So that's the antigen from which all these epitopes have come from. Here you see the icon, the Immunome Browser. If you click that, it's then going to map all the epitopes to a reference proteome. And this is what it's going to look like. Now let me walk you through this. You'll see 2 graphs. Once you do this, the first thing you'll see is 2 graphs. The top graph gives you a visual of the reference, so on the y-axis, the RF score, or the response frequency, along the position. So the x-axis is the residue. What I did was I overlaid the HCV polyprotein, so you can see what I mean. So residue 1 is the core protein, E1 envelope, so on and so forth, all the way through to NS5, which is at the C terminus. So you get the idea, that's what we mean. The response frequency of epitopes mapped to the entire proteome. graph below shows you essentially coverage, overall coverage by assay. So what do I mean by that? Well, sometimes you look at one of these plots and there'll be a gap. Does that gap mean that it hasn't been studied yet, or does that gap mean that it's been tested and it's a non-immunogenic region? That's what this graph down here will tell you. It'll tell you if there have been negative assays in that gap, then you know it's been studied and it's found for that particular house that you queried for, that it's non-immunogenic. You can then refine your search. As you can see, this is a forest of information. This is a lot of data. You still get a quick glance at, for example, there's a lot of reactivity to the core protein. Not surprisingly, it's the N-terminus, so it's probably the most abundant protein for that virus as the genome is translated. But you also see other areas of prominence. But what you can do is refine to eliminate certain things. You can specify a host or to differentiate. So you can say, just show me B cell data, or just show me T cell data, or just show me neutralizing data. You can get that specific. Now, if you scroll down on that page, this is the data table. And again, Julie's going to walk you through this in great detail. This just gives you an idea. If you were to scroll down, you get the table that is actually the RF scores per epitope year, mapped by position, their identity to the reference proteome, the raw number tested over number respondents, or number respondents over number tested, excuse me, the number of positive assays, the number of negative assays, and the raw RF score. All right, so now, with no further ado, Julia will be
good morning, everyone. My name is Julia, and I will be talking about Immunome Browser. So the purpose of this tool to allow users exploring how often each protein region has been studied in immune assays and how many assays the immune response was positive or negative. So basically, I iterate what Eddie just told you. And it's done through mapping and epitopes to the protein sequence, which we call a target protein or reference protein. And with advanced features which we add as a tool to the tool, you will be able to select any proteome or any target protein to map your clinical epitopes. So why Immunome Browser? It allows to summarize data because we have in database epitopes which are defined for different protein isoforms and different strains. So, and that's a way to bring data from those different antigens together to map to the reference antigen. So also the same different mutant variants, the same epitope are tested and reported in the data. So, and also Immunome Browser provides a way to look at them all together. So they will be represented to map as the same region in the antigen. So, and also immune response varies among studies or assays. So we cannot make some conclusions looking just at one assay. So, but when you look at the summary of data, we can make some conclusions about about some immune response. So first I will do overview, and I apologize for some repetition. So first we do, for example, the same query which Kerry showed you when you search for linear epitopes. And here I search for T cell assays and hepatitis C, and I selected for human. Then you click at the antigen tab, and for example, let's look at the epitopes at the map to genome polyprotein. So we click at the icon for Immunome Browser, and here is our page. So when even you selected positive assays only, so the tool grabs also negative data. Because as you can see, that graph makes only sense when we have both positive and negative data. So, and that's why you might be confused with different numbers. For example, here you can see that number. And when you go to to the tool, and if you scroll down, you will see the different number of epitopes. And that difference can be by two. First of all, not all epitopes have been successfully mapped. And second, negative epitopes is also taken from the database. So, and we will be providing here the next release. We will be providing numbers of how many epitopes we will map and how many positive and negative. So now what you can do, you can start playing with it. For example, you can delete a cursor, which you can move along the either upper or down graph. And for example, I put my cursor here. So, and on the right, you can see that I'm staying on the 400, position 400, and those numbers show the interval, lower bound and upper bound of 95% confidence interval, where I would expect my response frequency. So, and I will show you details how it's exactly calculated. But it's averaged over all, what you see here is averaged over all epitopes mapped to that specific position. In that specific case, position 400. And that specific position will be, in that case, it will be position 1200. So, and there are two definitions which I want to introduce. So, we calculate response frequency RF and R divided by N, where R is the number of responding subjects and N is number of tested subjects. So, and RF score ranges from 0 to 1, and that confidence interval, which you see, is a range of possible values that will contain the true value 95% of time if the experiment is repeated an infinite number of times under the same condition. So we expect that we have binomial distribution where we do T-cell or B-cell assays. And for each position, the numbers, those two numbers, is the range where you can have that score, the true score. So, and it also ranges from 0 to 1, and for that specific position, that interval will be in 1. So, we are not giving exactly a rough score because we want to correct for the sample size. For example, if you took some peptide and tested that positively in just one donor, we would have then a rough equals 1.0. And if another peptide was tested positively in 99 out of 100 donors, then we will have a rough 0.99, which is lower number. So that means based just on score, we would say, okay, the first peptide is more immunodominant than the second one, while it's not correct. So that's why we don't show a score, we show just confidence interval. And you can see that for some positions it can be pretty large, and for some it can be very small. So, and this just gives you the idea of how confident we are for a score for this position. So the bottom plot shows the number of positive and negative assays, again averaged over epitopes mapped to each position. In that case, this position is 400, and you can see the number of positive assays, 40, and negative 15. So, and the results which you will see are very specific. So, and I will show you an example. For example, we would do switch from T-cell assays to B-cell assays. So now we will be searching only for B-cell assays. Again, host will be human, organism hepatitis C, and we are searching for linear epitopes, and that's our result. So the numbers is different. So we have different number of epitopes mapped to the genome of polyprotein. And if we compare, you can see different numbers, different number of essays, different number of epitopes. If you look at the results based on the Immunome Browser results page, you can see quite different picture. So, for example, that region will have very, we can say, very immunodominant at the very beginning of the region, but not that much in the second half of the region of that. While for T-cell response, you can see not very high response by numbers, but it will be mostly in the middle of that region. Similarly, if you look at this, for example, we can see that we don't have too many T-cell epitopes mapped to that specific region of the proteome, but we have much more T-cell epitopes. Again, the tool allows to zoom. For example, you can zoom by selecting residue partition start and end at the bottom of the graph and click Update Display. So, and then you can focus just on specific region. And here you can see more clearly what's going on. If you compare the specific region for T-cell and B-cell epitope, you can see that in more fine detail that, for example, this specific region will produce very high B-cell response, but almost non T-cell response. And some regions, for example, never been studied in for B-cell response, like this one. So, and another example of specificity, for example, with all the same parameters, I just focus on acute hepatitis C using the disease finder. And so that's the result. Not so many epitopes were found. Again, we click on the Immunome Browser, and that's our picture. So now, for example, we do exactly the same, but for chronic hepatitis C. And that will be a little bit more epitopes mapped to that protein, and that will be the result. So now we can compare them side by side and look at specific regions. For example, this region, you almost don't see response, T-cell response in acute hepatitis C, but we see a lot of response in chronic. And the opposite, for example, in that case, we don't see any response in chronic hepatitis, but there is some response in acute. So that's how basically you can do research comparing different responses and opening Immunome Browser in different users. So let's go to details, how to read the table and how values are exactly calculated. So I will do it on the small example. So I did search for T-cell assays for Timothy graph allergen and using any host and any disease. So that will be the result. And let's focus on that specific antigen. And so it's just 90 epitopes per map. And let's look at Immunome Browser. So that's the picture we have. If you scroll down, you will see the table. So in the table, as they already mentioned, you can see all epitopes mapped to specific partitions and partition type here in the column, and the identity of the epitope to the source in the target protein. And also for each epitope, you can see the number of positive and negative assays. For example, in that case, it will be 2 positive assays and 0 negative. So it's a little bit tricky how we calculate those numbers. They are reported by reference. So basically, looking at those numbers, you can immediately tell how many references you reported for that epitope for your specific query. So, and if the reference had at least one positive assay, we will say that we have positive response coming from that reference. Also, the numbers for N basic subjects and responding subjects are, and final error score are calculated based on assigning the highest values from any positive essay. So I will show you here how it's done. For example, we have a query, and then we go to specific epitope. We focus on specific epitope and essays which are associated with the query. And we see that, for example, we have 3 references. And for example, first reference mentions 3 essays, which we query. For example, we query for T-cell assay associated with specific disease. And those numbers for N and R are listed here. So the top 2 will be positive essays because we have R not 0. We have responding subjects. And one essay, for example, it was from maybe even different study, but it was in that reference. We have N, for example, 100, but R 0. So that's negative response. And so what we do, we ignore negative. While in some cases it might be not correct, but we need to think what we are doing when we query. So, and we focus on the essay which shows the maximum N and maximum R number. For example, in another reference, there were 2 different essays reported. And then we take one with the maximum N number, and then R will be from the same essay. And for example, in that case, we didn't have any response, but there were 2 essays reported. Then we again focus on the maximum N. So what we do in the end, we sum up N and R numbers, so we will report in the table that that epitope has N equal 50, R equal 10, and we saw 2 positive essays and 1 negative. So now, okay.
What is that reference 3? Do you have a positive control for they're asking for?
No, for example, there was no. It's hypothetical.
They have a positive control. They know the asking for, and therefore the negative data.
Every publication is different. Most good publications should require positive control, but we don't control for that.
So
We don't capture positive.
So this could be somebody
Is that assay got it published?
Published in a bad journal.
That does happen.
Bad journal and database has a good article.
We're unbiased. We don't make those.
But also it's important to know the reality of most data. So you've got 100 overlapping pictures, and that's particular host. That's doesn't mean that happens.
Yeah.
Maybe that.
In the same sense, the negative data are hard to publish. You're always biased with positive data.
Yeah. So it's a hypothetical example. So, okay.
But not yeah.
Yeah, the question was if we are looking at the degree of response.
We have positive high, positive low, positive intermediate, but we only use those when the author is very clear about the high response. Here, often it's just positive negative, but the Immunome Browser doesn't matter.
Yeah. So, and the answer would be like if we count here for the degree of response. So, in the database itself, we report on the degree of response. But for Immunome Browser, we don't do that. So it kind of maybe simplifies view on what's going on, and in a while we will extend that and make it more specific. But currently, what we have, so we are giving user control everything what's going on by query. So, and that's what we specifically want to emphasize don't use the tool blindly, because what you see, it reflects what is in your query and which references will be pulled out and which assets will be looked up. So, and I apologize. So that's numbers you would see, and as I explained, they sum up for each epitope. So those numbers like N and R are summed up by epitope. So that means you won't find, if you go, so there can be desire to click on the epitope, to go here and to see exactly how those numbers were generated. So and I explained to you that it's not so easily done. So, and again, in this table, we provide this confidence interval for each epitope specifically. And I already discussed what that means, that interval. Okay, so when we, and for the bottom plot, you can see the number of epitopes. So, and again, they are summing up across epitopes. So what's going on? For example, that those epitopes I highlighted here, they all been mapped on this position A. So, and if you look at how numbers are generated, so all positive assets for those epitopes are summed up, so this will be number 5, and that's what you can see here. So, and the positive will be in blue here, and it will be number 5. So a negative asset, again, will be summed up across the epitopes which are mapped to the specific position, and that number will be 9, and this will be reported here, and here you can see that number 9. So that's how those graphs are made. Again, how the top graphs are made in response to the numbers in the table. Again, we look at this position 80 and the specific epitope, and we count the number, sum up the number of the subject cases, that will be our N, the total number of cases subjects, and the number of respondents, the 6. So then we calculate R score as R divided by N, and for this specific number, we calculate confidence interval, and that's what we report on the result. Okay, so some additional features. So you can play with the tool, zooming in and out using that boxes at the bottom. And you also can play by using your cursor and selecting any region on the either upper or bottom graph. And then it will be updated immediately rather than selected. And if you select that specific box, display graph residue position, then your table will be updated to correspond to the graph. And you can export results in an Excel file, which will look like this specific file. So that's all what I have.
One of our
I'll select epitope through the what does it mean? So yeah. This one. Yeah. So if you look at the RX score, we're around the set. And around the 1. If you take a look at score. However, if you look at around the 130, it is much more customized. However, at around And I don't know why almost the same picture. Yeah, so we see the, so in both cases we see the very large interval. So, and in both cases there are 4 intervals. So what we see from this section, we see that for 100 addition 100, our error score will be between this number and between this number. With very high confidence. So it's and the same here. It's slightly we are slightly in the high values, like from here to here. That's our interval where we can expect. So and if you go so below, we can see that we have a lot of not a lot. We have about 20 positive and very little negative essays, and we can hear another number. But those two graphs, they so they do not show exactly the same because as I explained, those show how many essays we have. And those graphs, they have nothing to do with each other. So that's why we show them together. So they do not correspond to each other from their number because they are calculated from completely different numbers. So this just shows that, like, that epitope was studied in so many positive and so many negative essays. But, for example, we had one positive essay with a lot of tested subjects and a lot of responding subjects. And, for example, just maybe one of those. And maybe here we just had less than, but again, we might have just one essay with many. So that's why we end up to see like almost similar pictures. So that's why we show you these two graphs, so you can get an idea, like in how many essays the specific conditions were studied or regions were studied, and what we ended up. Because as if you just look at just this graph, you don't get the whole picture. For example, you look at this region and you don't see any response, but it kind of sounds strange. Yes, we don't know if it was studied or not studied. And if you look at the this graph, you can see, oh, it was studied, but in all cases you just see any response. Okay.
It's important to point out that not all the data in the database has to come. While there are many assays, not all of them have the minority of the data. Human data. People don't. Again, the nature of the data helps us understand that there might be a great number of assays that we study, but the frequency data, maybe only half of the study has a process or maybe cheaper than one of those. So it's kind of the nature of the data that sometimes makes you think, well, what? So that's why go post graph there, because you want to know, explain why
the question was how to use what you can see in the result of Immunome Browser for selecting the epitope. So that's probably was the question from there. So basically, you can judge by, okay, so you can use all information in the table and information on the plot. So plots are here just for easier like visualizing the summary of data. But they do not provide you exact numbers. So if you go into details for each specific epitope, you can see in how many essays it was studied. For example, this was studied in 2 essays, and the number of tested subjects was 50, and none was response positive. So, yeah, so that's just to give you an idea about the whole process, but it wouldn't help you with selecting the epitope. need to go to the table. Yeah.
So the old version, and this is a new, again, this is being revamped and also improved as we go. Eventually, if you see on the top part of the table, all the columns at the top of the table, eventually you can sort on those.
Yes, so you will be able to sort.
Yeah, I think now you know that if you click on response frequency, it'll sort on.
Yeah. It's not here. That feature is not here. So yeah, that will be additional features. So yeah, I don't know So yeah, but you can export and then you can sort. But eventually, it will be able to sort in just here. And so if you focus on some specific region and you select some specific just here, and then you can sort for epitopes which map to that. So, and also, I probably forgot to mention that in very many cases, we, as Randy mentioned, we don't know N and R numbers, they're just not reported. What we do then? We assign, for positive cases, we assign N equal 1, R equal 1. So we just like one subject was tested and it was responded positively. If it was negative cases, we assign N equal 1 and R equals 0. So it was one subject and it was not responded. So, and it's probably, and if you scroll, for example, so if you, no, that's all good, but in many cases, you will see that it is just 1 and 0 or 1 and 1. So in many cases, and depending on your search again, so if you do very narrow search, like when you don't have too many data, then you will obviously see just a lot of zeros and ones.
So can I ask, once you zoom in on a subset of
you just click reset button. There is reset button, and everything will be reset. So it will be zoom out back. Okay.
It would read that had only one experiment longer, and there was just one experiment, nothing else. If you do 1 and 1 for all experiments, that you will type out. If you have only one experiment, or it was just when we had only one experiment. No, just
hypothetically.
So if at any position you had only one experiment,
Okay.
where you didn't know the number of responders or that, you said you put 1 and 1.
Yes.
So if there was only one experiment at that point, there was an RF of 1.
Yeah. That will be. The question was, if you have just one epitope with number of cases 1 and number of respondents 1, so and nothing else, what would be your confidence error score? Yeah, it will be 1, but the confidence interval will be from 0 to 1. So, what they do it from? They will be there. They will be there. Okay. Okay, thank you. So, and we are asking you to provide feedback, and let me discuss the tool and what it should show, and which additional features you want to see, and if it's clear or we can change something. Okay, so think about that, and we thank you a lot for providing you feedback.
We can share some live examples. Including